In this video, we will talk about K-means, the most famous clustering algorithm there is. Almost everyone can run it. Almost nobody can tell you why it works. By the end, you will be able to prove on paper that it must work and see exactly when it quietly fails. Now carry one picture the whole way through. A classroom full of students, no teacher, sorting themselves into study circles. This time, each circle has a leader, an imaginary average student whose mark sheet is the average of everyone in that circle. That average student is what K-means calls a centroid. The statistical translation worth fixing before we start. Each student is a data point. Their marks across subjects are a feature vector. A study circle is a cluster. The leader, the centroid, is simply the main vector of that cluster. And K is just how many circles we choose to form. K-means runs one strikingly simple loop. Every student joins the nearest leader, then every leader moves to the average of its new members, and we repeat. That is the whole algorithm. But two deep questions hide inside it. Why does shuffling leaders around ever settle down instead of wandering forever? And when it settles, is the grouping actually the best one or just a comfortable one? To answer either, we first need a number for what better means. So that is where we begin. Before an algorithm can chase a good grouping, we must say what good means with a single number. K-means uses the within cluster sum of squares or WCSS, also called the inertia. The idea is exactly what the classroom suggests. A circle is good if its students huddle tightly together around their leader. So for each student, take the square distance from their mark sheet to their circle's leader. Add that across everyone in the circle, then add across all the circles. That grand total is the WCSS. Written out, WCSS is the sum over every cluster K of the sum over every point X in that cluster of the squared distance from X to the cluster's centroid mu K, and mu K is itself the mean of the points in the cluster. Notice what this rewards. If every student sits on top of the leader, every squared distance is 0 and the WCSS is 0. The more spread out the circles, the larger it grows. So small WCSS means tight, good clustering, and the entire job of K-means is to make this one number as small as possible. Now one thing to file away. That square distance from a mean is the same quantity at the heart of variance. WCSS is really the total within cluster variation, measured from each cluster's own center. That connection is about to become the key of the whole proof. As a quick taste of the arithmetic, a circle of 3 students scoring 10, 15 and 20 has leader 15, squared gaps of 25, 0 and 25, and so contributes 50 to the WCSS. The algorithm that minimizes the WCSS is called Lloyd's algorithm, and it uses only the 2 steps from our loop, repeated. To keep the arithmetic clean, let us cluster students on a single test score. The steps are identical in any number of subjects. Now let us take 6 students. A scored 10, B 15, C 20, D 70, E 90, F 80. We want 2 circles, so K is 2. To give the algorithm real work, let us start it badly. Both leaders down low, one at 10 and one at 15. Step 1, the assignment step. With the leaders fixed, each student joins whichever leader is nearer. A sits on the leader at 10. Everyone else is closer to 15. So B, C, D, E and F all pile into the second circle. A lopsided split with a WCSS of 12,900. Step 2, the update step. With the students fixed, each leader moves to the average of its members. The first circle holds only A, so its leader stays at 10. The second averages 15, 20, 70, 80 and 90 to 55. Just from moving the leaders, the WCSS falls to 4,900. Now repeat. Assigning again with leaders at 10 and 55, B and C are now nearer 10. So they switch down. The split becomes A, B, C and D, E, F, the sensible one. And the WCSS drops to 2200. Update once more and the leaders become 15 and 80, taking the WCSS to 250. Assign a final time. Nobody is nearer a different leader, so nobody moves. And the moment an assignment step changes nothing, the algorithm has converged. Now look at our one number across every sub-step. 12,900, 4,900, 2,200, then 250, then flat. From a deliberately terrible start, it never once rose. That is not luck, it is what we will now prove. We watched the WCSS fall at every step. Let us prove it can never do otherwise, and that this forces the algorithm to stop. It looks heavier than it is. Two facts and a counting argument. The WCSS depends on two things: which student is in which circle, the assignments, and where the leaders sit, the centroids. Lloyd's algorithm improves one while holding the other still. So check each step alone. Fact 1. The assignment step. Leaders fixed. Each student is sent to the nearest leader. So each student's square distance is the smallest it could be. You cannot shrink a term by moving someone to a further leader. Every term is individually minimal. So their sum, the WCSS, cannot rise. Fact 2. The update step. Assignments fixed. We move each leader to the mean of its members. Why the mean? Because the mean is the single point that minimizes the sum of squared distances. A small theorem we can prove in 3 lines. Take the total square distance from the points to a candidate center C. Differentiate with respect to C and set it to 0. The derivative is twice the sum of C minus each point, which vanishes exactly when C is the average of the points. So the mean is the unique minimizer, and moving each leader to its cluster's mean drives the WCSS as low as that assignment allows. It cannot raise it. Together, the WCSS never increases on either step. It is monotonically non-increasing. It is also a sum of squares, so it never drops below 0. A quantity that keeps falling but has a floor cannot fall forever. The final nail is a counting argument. There are only finitely many ways to split n students into k circles, a vast number but finite, and each grouping fixes its own WCSS once its leaders are the means. Our WCSS marches downward through values drawn from that finite list, so it cannot decrease forever. It must reach a grouping where the assignment step changes nothing. That is the instant of convergence, and it must arrive in finitely many steps. KMeans always stops. Now read the fine print of that proof. It guarantees the WCSS keeps falling until no single step can improve it. But no single step improves it is not this is the best grouping possible. It only means we have reached the bottom of the valley we happen to start in. A local minimum, not necessarily the global one. Here is the trap. Picture 3 tight, well-separated group of students and ask for 3 circles. The perfect answer is obvious. 1 circle per group, a tiny WCSS of about 1.5. But suppose 2 starting leaders land by bad luck inside the same group, while a lone third leader is left to cover the other 2. Run the dance and every step behaves. The WCSS falls and then locks. But it locks with 2 leaders splitting hairs inside one group and one overstretched leader straddling the other 2. No student can improve things by switching, no leader by nudging. So the algorithm declares victory at the WCSS stacked near 101, while the true best was 1.5. It converged faithfully to a bad answer. Nothing broke, the proof still held, the problem was purely where we started. This is what KMeans++ fixes. A smarter way to place the initial leaders. Rather than scattering them at random, it spreads them out. Pick the first leader at random from the students. Then pick each next leader with probability proportional to the square of its distance from the nearest leader already chosen. Points far from every current leader are strongly favored. So the seeds land one per group instead of doubling up. That square distance weighing is the whole trick. It makes the algorithm reach for the far, lonely regions of the data when planting leaders. In practice, this one change turns K-means from something that regularly gets stuck into something that reliably finds the right valley. Same two-step dance afterwards, just a wiser place to begin. Now, two honest questions remain. We told the algorithm to make K circles, but how do we pick K? And once it finishes, how do we judge whether the circles are any good? Both fall straight out of the geometry we already have. First, choosing K. And beware an obvious trap. Since WCSS measures tightness, why not pick the K that makes it smallest? Because that game is rigged. Add more circles and the WCSS can only fall. And if every student gets their own circle, it hits 0. Minimizing the WCSS alone always say use as many circles as there are students, which is useless. So we watch not the WCSS itself, but how fast it stops improving. For 3 well-separated groups, the best WCSS runs 606 at one circle, 156 at 2, just 6 at 3, then 4.5, then 3. A huge drop down to 3 circles and almost nothing after. Plotted, the curve bends sharply at 3 like an elbow. That bend where extra circles stop buying real tightness is the natural number of clusters. The elbow method is simply reading the same WCSS that K-means minimizes. Second, judging the finished result. A good clustering is 2 things at once. Each circle is tight and different circles are far apart. The Davies-Bouldin index turns exactly that into a number. For each circle, measure its scatter, the average distance of members to their leaders. Call it S. For 2 circles, measure their separation, the distance between their leaders. Call it M. For any pair, form the ratio of combined scatter to separation, Si plus Sj over Mij. It is large when 2 circles are fat and close, the bad case, and small when they are tight and far apart. For each circle, take its worst partner, the largest search ratio, then average those worst cases over all circles. That is the Davies-Bouldin index, and lower is better. On our 3 need groups, the scatters are each about 2/3. The leaders sit 10 and 20 apart, and the index comes out near 0.13, small as it should be. Notice both tools read the same thing. The elbow watches within cluster tightness, and Davies-Bouldin weighs that tightness against the gaps between the leaders. Both are just readings of the centroid geometry K-means handed us. So the one idea to carry away. K-means is neither magic nor guesswork. It is a machine for driving a single number, the within cluster sum of squares, downhill. Every assignment lowers it. Every update lowers it. It cannot fall below 0. And there are only finitely many groupings, so it must stop. That is the whole reason it works. But it stops at the bottom of whatever valley you dropped it into, which is why a Y start like K-means plus plus matters, and why the elbow and the Davies-Bouldin index exist to check the result rather than trust it. So next time you run any clustering algorithm, ask the question that actually explains it. What single number is this thing minimizing? And could it be stuck in the wrong valley?